This is Shapira. He's the Business Development Director at CEVA. He's going to be talking about addressing 5G intelligent RAN using a dynamically multi-threaded vector DSP, as you can see. Looks like you're ready to go, Nurse, so I'll turn it over to you.
Okay, thank you. Can you hear me?
Yes, very good, thanks. Go ahead.
And can you see the entire screen?
Yes, we can see your screen.
Good, so I can start. So hello, everyone. And I'm very happy to get this opportunity to present for this audience. As Mr. Linley said, my name is Shapira, and I do business development for CEVA's mobile broadband unit. So that's where we develop our cellular baseband IPs for both the UE and the infrastructure side of the network. And today I will be talking about addressing 5G intelligent RAN using a dynamically multi-threaded vector DSP.
And Nur, could you turn on your camera so we can see you?
Oh, okay. Let me try to do that. Okay, can you see me now?
Yes, very good, thanks.
Okay. So I will start with a brief introduction to CEVA's 5G activities. So CEVA is a leading IP provider of wireless connectivity and smart sensing solutions. And for close to a decade now, we've been investing in this field of baseband technology for cellular infrastructure back from LTE and now going forwards to 5G NR. And CEVA established a tight collaboration with the tier 1 OEMs. It is publicly known that both Nokia and ZTE, they base their 4G and 5G baseband architecture silicon on CEVA technology. And also many other players and tier 2s use our technology for 5G small cell and V2X, Wi-Fi and whatnot. So CEVA has launched 4 vector DSP generations into this market. And here you can see our XC family of vector DSPs for baseband processing. As you can see, in each generation, we double the performance of the vector unit. So the first generation had a 32 multiply accumulate vector unit, and now with the recently launched XC16, which we launched at the start of this year, it has a 256 multiply accumulate vector unit. So while the first generations address both the UE side and infrastructure, then the latest XC12 and the XC16 were designed specifically for heavy infrastructure applications. So let's see what are the challenges and requirements for a DSP platform targeting 5G NR use cases. So we see an ever-increasing need for higher data rates and numerous operating modes. And this calls obviously for a scalable and a flexible architecture that can support, first of all, massive processing and aggregation to allow a large-scale baseband unit pooling and aggregation, and to accommodate the massive MIMO and advanced beamforming calculations. Then the architecture needs to address a wide range of network topologies. So the cellular network evolves from a distributed RAN to a cloud RAN and now virtualized. See all sorts of emerging open RAN-based architectures where you need a baseband or DU acceleration of COTS platforms like Intel's, or a lot of or architectures like massive MIMO radio units, and of course small cells in buildings. So it needs to cater for a wide range of use cases. And then one of the challenges with 5G is to really address a multi-user processing and being able to support very fine and narrow user allocations, and at the same time have a very short latency to accommodate URLLC operation and mission critical. And last but not least, there's the 5G standard or 3GPP standard that continue to evolve. We have now a release 15 being deployed in the field these days, but we expect a release 16 devices deployed in the upcoming years. So a hardwired solution will not do. One needs a robust SDR platform to serve this future run needs throughout the decade. So that is, for all these reasons, we introduced this, the new CEVA-XC 16, which is based on our Gen 4 XC. We designed that taking the design inputs from these leading tier 1 OEMs that deploy now 5G systems. But as I will show in a later slide, the XC16 is much more than a vector DSP. It's a complete subsystem by itself. And as you can see from the figure here, one can target the XC16 core to be embedded in either remote radio devices, like a massive radios, or from the central office or baseband unit device. So it is very well suited for both kinds of baseband processing. And this combination of a 256 Mach vector unit and really very fast clock speeds make it now a leading baseband crunching machine. And only recently, the Linley Group published this report affirming the XC16's position in the market. But it's not just sheer power, XC core or multi-thread operation, as I will show in a subsequent slide. So let's jump directly and have a look on the XC16 architecture. So here you can see the XC16 block diagram, and immediately you can see the XC16 has two separate execution units based on Scalar, two Scalar. Now, each of these execution units has its own program memory subsystem, with its own tightly coupled memory or level 1 cache. But what is interesting in this architecture is that the two execution units, they share the same data memory subsystem and other resources of this core. So the data memory subsystem has very wide memory bandwidth. So it has altogether 2048 bits per cycle that you can fetch or store to the local memory. And as you can see, it is divided into blocks such that the two execution units can access the local memory simultaneously without any contentions. At the heart of the architecture is these VCUs, vector computation units. So that's where you would find all the multiply accumulates and all the arithmetic logic. And again, as I will show later, these are shared in a very unique way by these two execution units. So this is like an 8-way VLIW machine. So you can imagine that in each cycle, and you can clock this thing at 1.6 gigahertz at 7 nanometer. So in each cycle, you can issue 8 instructions for 8 execution units across this very rich architecture. And on top of that, you enjoy all the usual CEVA architecture goodies, like the SoC controller that is handling a data movement into and out of the core. You can instantiate many AXI ports to access various parts of your system, and I will discuss that in later slides. So let's first touch upon this unique feature of the dynamic, what we call the dynamic multicore. So this is in fact the highlight of this Gen 4 architecture. It allows to do a dynamic VCU allocation that really allows to make very efficient use of this precious vector unit at the center of the course. So we support essentially 2 modes. In the one mode we call the QV mode or quad vector mode. You can see that all the vector unit resources are allocated to one of the Scalar processors, in which case the other processor still continues to act as a Scalar controller. And in the other mode, we call it a dual vector DV mode. That's where we do a symmetric allocation. So the resources are equally divided between the execution units. And what is nice here is that you could really switch between these 2 modes runtime with very few cycles. So if I want to illustrate the benefit from this kind of architecture, then this is a nice case in point. You can see here an example of a code running a channel estimation task for a 5G NR 4x4 channel. So as you can see, at least from afar, you can glimpse, a channel estimation is comprised from many subtasks, which means there's a lot of control code involved, even with this very math-intensive routine that is very basic for 5G systems. So here we can see the cycle count of what happens when you need to process a single user that gets the full spectrum of a 5G carrier, let's say 100 megahertz of a spectrum. Okay, so this is one extreme case, and you can see that this channel estimation will take like 300,000 cycles. Now, let's imagine a more realistic case where you have 16 users, and each one gets a narrow slice of the overall bandwidth. So now we're running the exact same code, but we see that the number of cycles more than doubles than in the case of a single user. So with this Gen 4 architecture, all we need to do is just switch modes. We switch from QV to DV. We run the exact same code. We don't change anything else. And as you can see, all the overheads from the control codes, they drop significantly as now they are shared by more than one execution unit. So this is very powerful for all sorts of multi-user use cases. So let's touch briefly upon each of the subsystems of the XC16. So we'll start with the first and foremost, the vector unit. So as you can see, we have 4 VCUs. So each of these has a 64, 16 by 16 multiply accumulates per cycle for an overall 256 max. And one can fetch 2,000 bits per cycle from local memory into this vector unit. So it's very, one can process huge amounts of data as are required from the use cases that we are targeting. The vector units also support the pseudo-floating point arithmetic to handle efficiently and also power efficiently cases where you need close to a floating point operation, like for instance for very large matrix inversion. And we can see here that the VCUs has several execution units. There's the VA, where you do the where you have all the multiply accumulates. There's the VB that does the high precision non-linear vector operations like square root or 1 over x. And here in this core, this unit can be, it's called a VAB, so it can do either more arithmetic stuff or some of these non-linear stuff. And I remind you that this is a VLIW machine, so each VCU can execute a different instruction. Then there are all the vector movement operations and the vector register file. So we have an orthogonal large 320-bit vector register file that is shared between all the VCU operations. If we go back to these scalar processors and that actually do this multicore, multi-thread operation, so they integrate, so the XC16 integrates dual CEVA-BX scalar processors, which is our latest generation common scalar architecture. So this is a very compiler-friendly architecture with a large common register file, full ISA predication, and a native support for all C types. And it is like a modern compiler based on the LLVM. It has quite a few code size reduction features. So we have all in all improved in this generation our control code performance and code size by around 30%. It also includes a second generation dynamic branch prediction, the BTB unit, with an integrated loop buffer. So all in all, you get a very efficient control code operation, which is a feedback we get from our customers. So typically, you know, we work with a tier 1 baseband vendors, but still they repeatedly say that the control code for layer 1 physical layer operations is very important in the overall mix of the layer 1 calculations. Regarding the data memory subsystem, so we have a very advanced data memory subsystem architecture. So it's designed to meet both the scalar control and the vector DSP bandwidth and latency requirements. So this TCN here that we see here, it can be, you can instantiate as much as 1.5 megabytes, and this supports very fast memory access, as I've said, clocked at very high speeds in 7 nanometer. And we've continued to improve our DMA mechanisms to support 2D and 3D DMAs that are operated by these queue and buffer managers that completely offload all the management of the DMA from the execution units. So you can really move data very efficiently into and out of the core. And this can be done by instantiating AXI ports. So you can instantiate, you have like one master AXI port, but you can instantiate several auxiliary master and slave ports to build all sorts of clusters and to have direct access to hardware accelerators. So all this, a lot of thought and design effort was made in this core with improving the pipeline and having predefined routing stages to really allow very fast operation in advanced technology nodes.
Hey, Nur, I know we got started late, but we do need to kind of wrap up the presentation. I know you got a few more slides left, but can you try to finish up quickly?
Yeah, sure. So maybe I will just give you like a feel of how the XC16 looks like within a 5G platform reference design. So here you can see this cluster of XC16s, and you can see them, they are connected using these auxiliary AXI ports to the between themselves and to the chip matrix. The platform also includes control DSPs or controllers for doing a tight PHY control operations, and a set of hardware accelerators that usually deal with some, typically with a forward error correction that still does not map well to DSPs, and this is also something that is part of CEVA offering. And you can imagine this cluster handling baseband processing. Can you hear me?
Yeah, you're back.
Because the actually my PowerPoint just crashed, I think.
We can still see your 5G baseband processing cluster slide.
Yeah, but I cannot skip slides now.
Oh.
Maybe you can. Oh, okay. Now it's better. Okay, so you can imagine. I've shown this new XC16 architecture. We've seen at the end how it looks like at the center of a 5G baseband processing cluster. So this kind of cluster can be used in either a completely embedded L1 application, as is in that case, typically you would embed another cluster, like an ARM cluster, to run all the L1 control code. And in another topology, which is very common now, you can use that as an accelerator to another platform, let's say an Intel platform. Okay, so many new vendors are now deploying a 5G RAN on top of Intel architecture. So over, like, let's say a PCIe link, you can accelerate and offload using our platform much more content than you would be with with typical acceleration options that are now in the market. So thank you very much, everyone.
Okay,
for listening.
Thank you, Nur. And I do appreciate your being able to start early. So thanks for that. We do have time for a few questions. Just a quick one from me. Nur, what's the status on this new product? Is the RTL available?
Yes, the RTL is available, and it is actually already licensed by a tier 1 customer that will tape out end of this year or early next year.
Oh, great, great. And then if anyone has questions, please submit them using the Q&A button at the bottom of your screen. We do have a question from the audience. You talked about a 30% code size reduction. How does that translate into silicon savings for the customer?
So the silicon savings are much more than just from this code size reduction. We see, you know, when you do the right mix of scalar and vector processing, we see like a 50% area reduction relative to, you know, previous generations with traditional architectures. But again, it very much depends on the use case at hand.
Okay. Let's see.
You can also take this next question. Okay.
Yeah. So another question from the audience. What kind of support does CEVA provide if someone wants to migrate their L1 application implementation from Intel FlexRAN to CEVA platform?
Okay, so here one has several options. What we provide is we provide a set of what we call software platform services that allows that we give an SDK that you can call this SDK from the Intel platform and invoke operations that are accelerated on the CEVA platform. So it's like a seamless integration, and you can gradually migrate functions from FlexRAN to the CEVA platform until maybe eventually you can, you know, migrate all L1 to the platform. So we give a software framework to help our customers do that.
Great, thanks. So another question from the audience: what is the die size? I guess they mean the area of your
area. Yeah, okay, so this is, of course, first depends on the process node, but this is information we prefer to share after NDA, not in this audience.
Okay. Another question. So the 1.6 gigahertz clock speed you were quoting is in 7 nanometer. Is it post PNR? What is the condition and what is the cells that you're assuming there?
Okay, so this is yes, it's post PNR, and as I've said, we are working closely with this customer that is will tape out very soon. So we know this speed is achievable. I don't know offhand what is the condition.
Okay. Yeah, what technology node is the solution available in? I assume you can port this to any.
Yeah, it's a soft IP. Tier 1 customers would for sure use that in 7 nanometer and soon in 5 nanometer as well. But we think that it's also relevant for 12 or 16 nanometer. We see customers with interest in that as well.
Okay. And question about, can you please tell us about pseudo floating point arithmetic?
Yeah, so with the pseudo floating point, you have like a 16-bit mantissa, and then for, let's say, an I and a Q for a complex number, and then another a 16-bit that is common for the exponent. So the vector arithmetic unit can still, in that way, can still do, in fact, integer arithmetic by just multiplying the mantissas and doing this, some kind of a normalization from the exponent, but still it does not change significantly the power consumption of the core, and still give you a good performance. And we can show that we have very good SNR for all the required operations now for 5G NR and massive MIMO.
Great. All right. Well, that's all the questions we have. So I'd like to thank Nur for giving this presentation and for stepping in. He'll be appearing later today at a breakout session if people have more questions or want to hear more about the XC16. So thank you, Nur.
Okay, thank you very much. My pleasure.